be telling us about this fortuity in the bulk. So anyway, take it away, and hopefully the Zoom should work. I think the live streaming should work as well. So thanks a lot for accepting to give this talk. It's very early, right? It's 6 o'clock in California, so.
Oh, actually, I'm at Colorado right now, so it's 7:30. It's not too bad.
Okay, it's not so bad. Okay, great. Okay.
Okay, great. So thanks for the invitation. Today I'll talk about the fortuity in ADS3CFT2. I have to apologize first that I got the code this morning, so I hope I will perform well. Okay, good. So the talk is based on the work with Qiming and Yin, and some work in progress. Oops. Okay. I'll make a very brief introduction, then I'll start to talk about D1, D5 CFT. Holography is a powerful tool to study quantum gravity, and to overcome the nature of strong-weak duality, we will focus on the BPS sector in this talk. And the recent proposal by Zhang and Lin, they offer new insight into the understanding of the BPS states. Let me briefly review what they proposed. So for a dual family of CFTs labeled by N, they propose to classify the BPS states into two categories: monotone states and fortuitous states. So there are two pictures here on the slide. The left one corresponds to the monotone states, the right one corresponds to the fortuitous states. So let me explain the picture a little bit. So monotone state, so at a finite N, if you have a monotone state, then this monotone state can be extrapolated to infinite N and disassemble into product of non-interacting supergravitons. However, if you have a fortuitous state at finite N, it might remain fortuitous as you increase N, but at one point, let me call it N star, it will lose its BPS property and become non-BPS. So these fortuitous states, they are expected to reproduce the black hole entropy. Okay, so in this talk, I'm going to focus on the ADS3CFT2, and I will also mention what are the similarities with the include super YAMLs and what are the difference. So type 2B string theory on ADS3 times S3 times T4 with Q1, Q5 units of R flux is dual to a CFT that sits as a modular space of symmetric product orbifold theory of T4. And it also has a label N. It's N equal to the product of Q1 and Q5. At symmetric product orbifold theory, the degeneracy of low-lying states, they grow exponentially with energy. It's too fast. It's a bit different from the sub-exponential growth expected in supergravity. And it's believed that by turning on an exactly marginal deformation, most of the low-lying states will get enormous dimensions to make the BPS spectrum compatible with the supergravity interpretation. Okay, so this is my short introduction of ADS3CFT2. And so the plan of this talk is I will review what are the Hilbert space of the symmetric product orbifold. Then I'll turn on the exactly marginal deformation to see what BPS states will remain in the spectrum and what states will get lifted. To do that, I will introduce the supercharged cohomology. And then I will further classify it into fortuitous cohomology and monotone cohomology as Zhang and Lin did in their earlier proposal. Finally, I will make some comments on how to construct fortuitous states at larger N using smaller N data. Then I will make some remarks about future directions and things. So let me explain what is a T4 sigma model first, as we will focus on the symmetric product orbifold of it. So the T4 sigma model is a system of 4 free bosons and 4 free fermions. As you see, I write down a bunch of fields. So this X mu goes from 1 to 4, denotes the 4 free bosons, and there are 4 left moving fermions and 4 right moving fermions. Well, the Hilbert space of this T4 sigma model is just by doing the standard quantization of 4 bosons and fermions and acting on the ground states, and then you will get the Hilbert space of it. Now, let me talk about the Hilbert space of symmetric product orbifold. This part will be of certain importance as later, since the whole talk is based on what states will remain BPS after you turn on that exactly marginal definition. The Hilbert space of symmetric product orbifold is a sum of twisted sectors. And each twisted sector are labeled by the conjugacy class of Sn. And for each Hilbert space corresponds to the conjugacy class, it's the direct sum of the Hilbert space of this group element in the inside the conjugacy class. And the Hilbert space of Hg, which is G is a group element of conjugate class Sn, is given by quantizing the product theory T4 to the power of n on S1 with twisted boundary conditions xi as you go along the circle for 2 pi, then you will be mapped to a new x, which is related to the previous x by group element acting on that label. And this Sn here, they denotes the Sn invariant projection. I will be more clear. The group element of G of Sn can be decomposed into product of cycles. Here I write a generic group element and write it into products of cycles. Here a cycle from A1 to An denotes a permutation that sends Ai to Ai plus 1, certainly at the endpoints starting from An to A1. From here, we see that the Hilbert space of this symmetric product orbifold will factorize. And therefore, we have for this group element G, the Hilbert space corresponds to G equal to the direct product of Hilbert space for each cycles. And the Hilbert space of each cycle can be derived by studying the Hilbert space of T4 CFT on circle S1 with radius Wn. Wn here denotes the length of the single cycle. And then the Hilbert space of Hwn is spanned by acting these fractional modes on the twisted ground states. So this will give you the Hilbert space of Wn. Then you take the direct product, then you form the Hilbert space of Hg. Then using the previous prescription, then you can get the Hilbert space of symmetric product orbifold of T4. Good. So at the orbifold point, the theory has a contracted large n to 4,4 algebra. And let me not delve too much into the details, but here's the OPE between free boson and free fermions. And you can find the other superconformal algebra by doing the standard quantization of these elements, and then you find this is a stress tensor, and these are the 4 left supercurrents, and this K denotes the SU2R currents. So now let me, after talking about the Hilbert space of symmetric product orbifold point, so let's specialize into the states that has a BPS property. So as I said, it's n equal to 4,4. It has an n equal to 4,4 algebra, so it has 8 supercharges. And more specifically, there are 4 left-moving supercharges, and there are 4 right-moving charges. If you pick the left-moving supercharge or the right super-moving charge, and you study the anti-commutator between the supercharge and the supercharge dagger, then you will get you will find it's equal to the holomorphic weight minus the holomorphic R charge or the anti-holomorphic one. So we call the states that are quarter BPS. They have H tilde equal to J tilde or H equal to J. Here, H tilde and J tilde are like anti-holomorphic weight and R charge. And half BPS states are H equal to J and H tilde equal to J tilde. Let me be more specific with what are the half BPS sectors at the orbifold point, as they will play an important role later. So as I said earlier, like you can construct the whole Hilbert space of symmetric product orbifold just by studying the single cycle BPS states. And the single cycle half BPS states, they form a representation of the left moving and right moving Clifford algebra here. And so I write down this W plus minus plus minus plus minus plus minus. Here, it denotes a single cycle half BPS operator. So they can have left moving H equal to J equal to 2 over W. So the length here is W. Is the bottom component of this thing is W minus 1 over 2. And then you can increase it by half, half, and 1 finally. So you will have a quartet by the Clifford algebra for the left moving sector. Similarly for the right moving sector. And the multi-cycle half BPS states, they can be constructed from taking the product of single cycle half BPS operators. They also form a representation of the diagonal Clifford algebra. In this talk, we will focus on the quarter BPS states that are the right moving BPS. Namely, we will consider the excitations on the left moving sector, on the left moving BPS. We will consider excitations on the left moving ground states, such that it's left moving, non-supersymmetric, but it's right. It's not left moving BPS, but right moving BPS. Good. So this more or less concludes my introduction to the symmetrical product orbifold, the Hilbert space of it. So if you have any questions, let me know. Okay, good. There are no questions. So I will proceed.
Wait, sorry. Actually, I have a question. Are we going to be focusing on the Ramon sector or the NS sector in this talk, or both?
We focus on the NS sector. Well,
Okay.
yeah, in this talk. So we can study, as I said earlier in the introduction, we can study the D1, D5 CFT by deforming away from the orbifold point and study how the spectrum will get, how the BPS states, whether some of them will get lifted and some will not. So D1, D5 CFT here is given by deforming the symmetric product theory by an exactly marginal deformation phi. And is constructed by acting supercurrent mode on the half BPS operator in the length 2 cycle. And this will give you an exactly marginal deformation, and you can turn it on and deform it away from the orbifold point. Then we are interested at how the anomalous dimension spectrum and will be, and what are states that will not get lifted. The holomorphic and anti-holomorphic anomalous dimensions are, let me label them as delta H and delta H tilde. They will satisfy delta H equal to delta H tilde just because the anomalous spin will be equal to delta H minus delta H tilde, and we don't want to have anomalous spin, so this forces delta H equal to delta tilde. Therefore, delta H can be computed by studying the delta H tilde, and this is equal to the right moving L0 minus K0. Yeah. And using the algebra we mentioned earlier, you can be writing as the anti-commutator of the right moving supercharged and the right moving supercharged dagger. So since we are interested at understanding the BPS states, we want to understand what is null space of this anomalous dimension matrix. The reason why it's a matrix is because there are a bunch of operators at the orbifold point. They have the same quantum numbers. So after you deform away from the orbifold point, you need to be careful to and study the lifting matrix instead of yeah. And the BPS states will correspond to the null space of its lifting matrix. And according to the standard argument that BPS states will be in one-to-one correspondence with the supercharged cohomology here, namely the states that are supercharged closed but not supercharged exact. Good. Here, for the moment, we will focus on the second order conformal perturbation theory for the lifting matrix, but we will later provide a non-renormalization conjecture such that it goes to order for certain cases. And for the quarter BPS states at the orbifold point, it's enough actually to just consider the first order deformed supercharged action to reconstruct the second order lifting matrix. The reason is because the right moving supercharge and the supercharged dagger will annihilate the right moving or the zeroth order right moving supercharge will annihilate the right moving BPS the right moving BPS operators. So therefore, you only need to consider the first order deformed supercharges to study a second order conformal perturbation theory. It's also interesting to work out the anomalous dimension spectrum for the non-BPS states, but this will not we will not pursue it here in this talk. I think I more or less conclude the setup of this deformation. So then I will start to explain what are the deformed Q action, what are the deformed right moving supercharged action look like. Good. So here I omitted a lot of details, but so hopefully I will just talk about, I will explain what are the effects of the Q action. The supercharge, the right moving supercharge Q, it has a certain decomposition into four different Qs. Here I write 4 different Qs, and here 0 means the Q action that does not change the number of cycles, but here 1 means like it will increase the length of the cycle. So just to illustrate, Q0, 1, it will increase the length of here it's a cycle of length W. Q0, 1 will increase the length by 1 to W plus 1. And yes, good. And also note that here the right moving R charge will go from W minus 1 over 2 to W over 2. And the Q minus 1, 0, they can join 2 non-trivial cycles. As I mentioned, this 0 means like you will not change the total length, but you will reduce the amount of cycles. So you can join 2 non-trivial cycles. One is of length W minus N, one is of length N to a cycle with length W. And Q1, 0, similarly, you can split a non-trivial cycle into 2 non-trivial cycles. And the Q0, minus 1 will split out a trivial cycle. So you reduce the length of W to W minus 1. I want to make 2 comments here. At infinite N limits, if you analyze the scalings, you can find that Q0, something will dominate over the other Q. Another comment is, unlike for super young males, the supercharged action in this theory does not obey the Leibniz rule. But we will also see that at infinite N, if you only restrict to Q0, something sector, then you obey the Leibniz rule. Okay, good. So I will start. Okay.
What is the dependence of the anti-commutation relation between Q and Q dagger on little g?
Little g.
The deformation parameter.
Deformation parameter. Oh, so here the anomalous dimension. If you write it down, I think because we are doing perturbation theory, so there must be some kind of. Okay, so the first order Q deformation, if you analyze it, then you can find that it depends on the G. The coupling G here, the coupling G. Because it's essentially you analyze how the Q acts on a state, then so if you think about in terms of how to say it, you can do a series expansion for that Q action. Then that Q action can be written as a series expansion order by G. Yeah, okay. So in the end, if you analyze the first order deformed Q, so here Q and Q dagger, both of them will have a G dependence, then delta H will have a G squared dependence. Did that answer the question?
But I'm trying to ask how 12 depends on G non-perturbatively as a function of G.
You mean how the Q action?
I guess so.
Let me see how to answer this question.
Well, you can return to it later. We can defer.
Okay, good. I have a formula in mind, but I didn't print it on the a slide, so I don't know how to say it very quickly. Okay, hopefully I will return to it at one point. Good. So I will focus on supercharged cohomology at n equal to 2 for the moment and give a bunch of observations at n equal to 2, and hopefully then I will make some conjectures about how the supercharged cohomology, how the degeneracy of supercharged cohomology will behave at a generic n. So at n equal to 2, Sn will just reduce to Z2. So there will be operators of two different cycle shapes. One corresponds to the non-trivial Z2 action. I denote here as 2, and one corresponds to the identity. I denote here as 1, 1. The right moving BPS states in the let me call this as maximum twisted sector and this as untwisted sector. The maximum twisted sector, the right moving sector, they form a quartet with H tilde equal to G tilde goes from half to 3 half. And operators of cycle shape 1, 1, the untwisted sector, they can be further classified into 4 different quartets by utilizing the diagonal Clifford algebra. So here I write down 4 different quartets, and here S means it's right moving, totally symmetric. So there are 2 sectors you can find. One is the H tilde that goes from 0 to 1. Here is a typo. And another is from H equal to 1 to H equal to 2. And there are another 2 sectors that are right moving antisymmetric. They have H tilde equal to G tilde equal to from half to 3 half. It might be a bit weird to think about right moving antisymmetric sectors since we are focusing on the symmetric product orbifold. But if you make the left moving sectors antisymmetric as well, then you will get a totally symmetric sector. So the interesting thing is this antisymmetric sector, it has the same right moving R charge as the maximally twisted sector. This will later play an interesting role. Good. So because we have the supercharged action and we have the Q square equal to 0, we can study this how the supercharged action, how the supercharged acts by just writing down the supercharged quotient complex. And as we explained earlier, there are 2 major effects of the Q action. There are joining process and there are splitting process. So if you follow the R charge conservation, and if you follow the joining splitting rule, you can find that different sectors are related by Q as in the picture. Nothing can map to the 1, 1 S1 sector. 1, 1 S sector can map to the maximum twisted sector, and it's through a join process. And the maximum twisted sector can be split into a symmetric sector. And then 1, 1 S2 can be mapped to nothing. Yeah, you can map to nothing. So it's automatically Q closed. And here 1, 1 S1 is automatically not Q exact because nothing can map to it. And for the antisymmetric sectors, it's a bit more interesting. So at the perturbation level, acting Q on it can map to nothing, and and it can not be mapped to 1, 1 antisymmetric by acting Q on something. So this says all the 1, 1 antisymmetric sectors are automatically BPS even after they deform away from the orbifold point. So it's like frozen, and so you will always remain there. And let me explain the first chain a bit more. Here, I will try to motivate a non-renormalization conjecture by studying the first chain, well, of course, and also the second, third chain. For N2, the D1, D5 CFT is a bit different from N bigger than 2. The reason is that the elliptic genus here is a modified index. Actually contains the full information about the BPS spectrum. Namely, you can write down a BPS partition function for it instead of the modified index. So it gives you more controlled information about the degeneracies. There are no cancellations. You can derive the exact BPS partition function by making a mild assumption that there is no symmetry enhancement at generic points on the conformal manifold. The idea is based on these two papers. And what we observed in our paper is that if you analyze the Q cohomology, and you can find the degeneracy of BPS states agrees with this exact BPS spectrum up to h equal to 4. Hence, therefore, we could make the following non-renormalization conjecture that the spectrum of BPS states in the D1, D5 CFT is determined exactly by the lifting matrix at the second order without any higher derivative corrections. I also want to leave a question here, namely how to check this conjecture at n equal to 3 by just doing the second order conformal perturbation theory. The reason why we might make this conjecture at n equal to 2 is we have all the information about the partition function, but at n equal to 3 we lose that property. So for the moment I don't know how to check it if I just do the second order conformal perturbation theory. Another interesting observation by studying the supercharged cohomology at n equal to 2 is you can observe there is a R-charge concentration going on for the BPS cohomologies. So all the quarter BPS primary states, when I mean primary, I refer to the contracted n equal to 4,4 algebra. From there, you can define the notion of primaries and its descendants. Here, all the quarter BPS primary states at n equal to 2 are sharply concentrated on a single cochain in the complex, the middle one. So let me see if okay. So if we go back to this slide a little bit, so what I'm saying is all the quarter BPS states primaries at n equal to 2, they are at this maximally twisted sector, they are at this antisymmetric sector. There are no quarter BPS primaries at 1, 1 S1 and no 1, 1 S2. In other words, the degeneracy of BPS states at n equal to 2 will dominate if a given quarter BPS state has the same right moving R charge as the maximally twisted sector. Here's some evidence and the observation. So if you write down a D1, D5 CFT partition function, you can, so here I need to explain a little bit about what are all these things are. So here chi0 and chi1 are two short characters correspond to that n equal to 4 contracted large n equal to 4, 4 algebra. And here chi2, 0, 3, 0, 4, 0 are like the long characters. And here chi bar S1, chi bar S2 denotes the right moving quartets for 1, 1 Si. And here chi bar A denotes the right moving quartet 1, 1 AI and the maximum twisted sector. It's really because these two sectors, they have the same right moving R charge that you cannot distinguish them at this level. So we can make some observation that this is all the quarter BPS states at orbit. So at the orbifold point, all the quarter BPS primaries in the 1, 1 S sectors, they will combine with the primaries in the maximally twisted sector. And after the deformation, they will get lifted. The evidence is just like there is no such long characters in front of the right moving quartets 1, 1 Si. Because here you see the long character only appears in front of this chi bar A, which denotes the right moving quartets for these two sectors. And all the quarter BPS states primaries are in the middle chain middle cochain as we just explained. Further evidence is that I need first of all I need to make sure that there are long characters for 1, 1 S at the orbifold point. So if you do at the orbifold point, if you do the partition function decomposition, you will find that at the 1, 1 sector there are indeed a bunch of long characters at the orbifold point. So what happens is essentially, as I said, it combines with the maximum utility sector, and it will disappear after you deform it away from the orbifold point. If you do some math calculation, you will find that it's true, and it will match the D1, D5 CFT partition function. So some people here might be interested at the ratios between the quarter BPS primary degeneracies at the antisymmetric sector and the maximum utility sector. So at least at n equal to 2, the ratio here is the degeneracy of 1,1a over the maximum utility sector. The ratio will decrease in general, but at least at h equal to 7 is still remains finite, which is 0.1. Okay, good. I want to make a conjecture about how the R charge concentration work for n bigger than 2. So essentially, you'll be the similar idea. So I want to conjecture that all the quarter BPS primary states are sharply concentrated on a single cochain in the complex. Namely, the degeneracy will dominate for the states with the same right-moving R charges as the maximally twisted sector. This is a mild version of the story I heard from other people, that all the states that could get lifted will get lifted. Here, I mean, for example, like if these states could combine together and form a non-multiplet, some people expect it will get lifted. So roughly speaking, what I'm saying is if we think about the n-3 supercharged cochain complex, so here there is an untwisted sector, here there is a twist 2 sector, here is a maximum twisted sector. I'm saying that similarly, there's another one similar to the 1,1a. So I'm saying that the sectors that with the right moving R charge as the maximum twisted sector, the degeneracy will dominate, and the degeneracy will sharply concentrate around this region. And I'm working on checking this conjecture right now. Good. So here I complete my discussion on the degeneracies of these BPS cohomologies. So are there any other questions?
Yeah, I have a question.
Okay.
Could you just elaborate on what you mean by this being a mild version of this statement? That it's a statement.
Oh, so I guess let me go back to 1,1. It's include 2 picture. So because we know that it's 1,1s1 and 2 and 1,1s2, they could combine together and form a long multiplet at the orbifold point. So if all such states will get lifted, then there will be no quarter BPS primaries at for D1 D5 CFT at after deform away from the orbifold point. So the degeneracy will dominate at this maximum utility sector. Did that answer the question?
I think so.
Okay, thanks. So now let me talk about the monotone and the fortuitous, and we could further classify the quarter BPS cohomology classes into 2 classes: monotone cohomology class and the fortuitous cohomology class. We have here I'm providing a new definition of monotone and fortuitous for the D1 D5 CFT. It's a bit different from the definition in our paper. So now we want to say that a Q cohomology class and rank n is said to be monotone if for all n prime bigger than n, there exists a lift for the state to H Hilbert space of n prime such that the lifted state is also Q closed. Otherwise, we call the Q cohomology class fortuitous. Let me be more precise about the details on the lift, and I will provide an example that will make things simple. So consider a D1 D5 CFT of rank n prime which greater than the rank n of the D1, D5 CFT, which we are interested in. We can define a stringent exclusion principal map by projecting the Hilbert space from Hilbert's n prime to n. And so how this works? So we can think about the group elements of Sn prime at Sn. So certain elements in Sn prime are related to the group elements in Sn. So from here, we can define a projection relating these two sectors. So there are two cases, of course, for Sn prime. There will be a group elements G prime, which permutes the label between n+1 and n prime. Then we define this stringent exclusion principal map projects out all such states. But for the group element that has trivial action for the labels n+1 to n prime, then we see we define it to be that it will have non-trivial projection. So you could find a subset of Hilbert space in G prime that equal to the Hilbert space G, and take the direct product with trivial identity operators. Good.
Can I ask?
Yeah.
So what if you have permutation between the one from n+1 to n prime? Like, so you have a twisted Hilbert space, but only on the indices from n+1 to n prime. I guess you still have like a projection, which would be non-trivial, right?
For n+1 to n prime.
I mean, here you have just one cycles and you have like nothing's happening here, but you could consider G prime to be G times some permutation of like a product of permutation. For example,
I will also say that these states will be projected out as these states are non-trivial excitations on from the regime n+1 to n prime.
Okay.
Thanks.
Sorry, okay, I don't understand the notation. For example, in the first line, G prime not equal to G n+1 n+2 total to n prime. What does this mean? Can you explain?
Oh, okay. Sorry, I guess I didn't write the notation clear. So here I simply mean that if the G prime permutes, so because we have like n prime copies of T4 now, and I require this G prime does not permute any indices between n+1 to n prime.
Doesn't commute? Can you say it again? Doesn't.
For example, like because this group element could switch the indices or permute the indices. Let's see how. So I want G prime action. It does not. So I have copies of T4 between n+1 to n prime. I don't want my G prime to change them.
Okay.
Like I just want to, yeah.
Sure. Yeah.
And this is what I mean here.
Maybe I can comment to address the question. So this is a cycle notation for symmetric elements, and each of the brackets denotes a trivial element of a trivial cycle of the permutation of elements. So these brackets all are trivial cycles which act on the extra copies.
Right.
And G is any combination of cycles on the first n copies.
So are you saying that if you have just trivial, okay, if the nth through n primed strands are all vacuum strands, then you can descend, you can project down.
Yes, that's what I'm saying.
Oh, okay. Okay,
thanks. Yeah.
So sorry.
Okay, here. Sorry.
Sorry, just to clarify, do they have to be vacuum strands or just strands of length 1?
So if there are excited states, I will also project them out.
Excited on the additional strands?
Yeah, on this additional string.
Okay.
Yeah, thanks. So let me provide you an example of the lift. So given a BPS cohomology class at n equal to 2, let me write it as this UI and 2i. So we know. So let me for the moment just talk about Q closeness, not talk about Q exactness, but the discussion will be similar. So we know that at n equal to 2, if it's a BPS cohomology, this means it's Q closed. And we know at n equal to 2, this length 2 operator, it could be split into 1, 1, like the untwisted sector. But we don't have this Q0, 1, which increase the length by 1, because at n equal to 2, the maximum length is 2. So automatically, we know that the splitting process for this operator is closed, Q closed, but we don't know if if I want to extend the length by 1, whether this is still Q closed. So I don't know if the Q0, 1 is closed. If there is no such a state at n equal to 3, because at n equal to 3 that I could I could include other states which has non-trivial excitations on the third copy. If I can find if there is no such state that satisfying this relation, namely the Q action that extends the license. So there are effectively 2 Q actions. The first one increase the length of 2 to 3. Another is to join these 2 cycles to form a cycle of 3. So if at n equal to 3, if you can find no such state such that these 2 effects cancel, then we will say that this state is fortuitous. Is that clear? So here all I'm saying is that at n equal to 2, the BPS condition is weaker than the BPS condition at n equal to 3, because at n equal to 3, there will be another condition, namely you can increase the length of the cycle length by 1. But this effect, you will not be able to see it at n equal to 2. So there is another layer of complexity you need to worry about at n equal to 3. So now I'm saying that if you can find such a lift, namely you can find some non-trivial excitations on the third copy and non-trivial excitation on the twist 2 operator, twist 2 sector, to make this new state to be Q closed at n equal to 3, then I will, if you cannot find such state, then I will say that this state at n equal to 2 is fortuitous. Another comment I want to make is if you act the projection map on this operator, you will only get an operator. If you project from n equal to 3 to n equal to 2, then you will only get the operator of length 2. Okay, so I hope this will be clear. Good. If such lift indeed exists, then one might ask a question: can you lift this to n equal to 4? Like at n equal to 4, can you still find a new combination of operators such that it's Q closed at n equal to 4? So there will be multiple versions of calculating this fortuity. So the best situation will be at n equal to 3 that you couldn't find for all the fortuitous states, you couldn't find such a lift. Then you will claim you can claim the victory that you have identified all the fortuitous state. And another comment is that the lift is not unique. So different states at n prime bigger than n could project down to the same state at n. Another remark I want to make is at n equal to 4 super Young Mills, the Q action and the so-called stringent exclusion principle, namely the trace relation, it commutes. But at n equal to and D1, D5, Q and pi does not commute. So this leads to some difference. Now, since there are
is that because the trace relations are something, that I can always write the Q in terms of products of traces, like the trace relations have nothing to do with Q. Or can you explain that statement, why it's different in n equals 4 than here? Or
okay, for the moment, I only remember the conclusion. If I think a little bit, maybe I will give you an answer, but I can tell you why at D1, D5 it does not commute.
Okay. Is it this pi seems very violent. This operation just kind of forgets things. So yeah. Okay.
I guess a good example would be you can think about a non-trivial state of some kind of form like this 2, 1. Then you can if you act Q action acting on it can give you some state of the cycle shape 1,1, like on twisted sector. But the stringent exclusion principle on the left side will project out, if you go from n to 3 to n to 2, you can project out the 2,1, but you cannot project out the 1,1. So then you will have something like 0 maps. Yeah, okay, thanks. So let me explain the large N cohomology, and this is a so-called multi-graviton cohomology. Under the ADS-CFT correspondence, the quarter BPS single graviton states, they correspond to the single cycle half BPS states, and their left moving SU 1,1/2 global descendants generated by these global modes. These are like, it's a subgroup in the algebra I just mentioned. And the single cycle quarter BPS operators, they are dual to single gravitons. And at infinite N, Q action satisfies the Leibniz rule. Therefore, you can generate the multi-cycle BPS states by just combining the single cycle operators. Hence, we conclude that at large N, actually, this is infinite statement. At infinite N, the cohomology are the multi-graviton cohomology. So we want to ask a question: what are the multi-graviton cohomology at finite N? So we know that if you decrease N, the gravitational interactions will increase. So therefore, one will expect that the multi-graviton form at infinite N will get modified by the finite N effects. So what we have observed is that the multi-graviton states at finite N can be corrected to supercharged closed states and represent monotone Q cohomology classes. We also observed that multi-graviton degeneracy at finite N matches with the degeneracy of the larger cohomology for certain operators of certain cycle shape. Good. So there is a puzzle actually. So one thing is multi-graviton partition function. Because of the previous prescription at large N, so you can restrict to the set at large N. You can restrict to sectors of this length 2 and 1,1. There are only two non-trivial excitations. Well, there are only 2 copies with non-trivial excitations. The multi-graviton partition function at n equal to 2, it actually does not exhibit a contracted large n equal to 4,4 character decomposition. Naively, one would expect that the multi-graviton will count the degeneracy of monotons. As pointed out by Hughes and Shijimori, boundary gravitons also need to be taken into account at finite N. So their results actually takes a neat form. So if you recall that the D1, D5 BPS partition function I wrote down, so there are this K0, K1, there are 4 characters. So this and these 3 red color elements, they are half BPS operators and their descendants, like not just global but also local. So what they found was if you take into account of these boundary gravitons, then these multi-gravitons plus boundary graviton, they will have a neat form just by the short character. So you will find more details in their talk, and let me not explain too much about it. But this also raises a new puzzle. So this means there are new extra BPS states at finite N. For example, if you act on some local local mode of the algebra on some multi-graviton, it's also BPS. But in the infinite limit, we know that multi-gravitons will always already give all the cohomology classes. So this means if we include the contributions of boundary gravitons, we will get a partition function that exceeds the infinite partition function, infinite graviton partition function. A possible explanation is that a linear combination of these boundary gravitons dressed with multi-graviton and other multi-graviton wave functions will become Q-exact in the larger limit. This can reduce some degeneracies. Good. So I want to make a conjecture about monotone cohomologies. This conjecture actually is based on the intuition that the contracted large n equal to 4 common form algebra will be preserved after the deformation. Therefore, if you find this multi-gravitons they are monotons, so the local descendants of these monotons should also be monotons since the local algebra is preserved. The conjecture I want to make is all the monoton cohomology class at finite n can be represented by finite n quarter BPS multi-graviton states and their descendants under the Lefter conformal algebra. So this will be the best situation. So what's the consequence of this conjecture? So if we go back to the previous slides for the D1, D5 partition function, so if these sectors denotes all the monoton classes, then this means all the quarter BPS primary states are fortuitous. Also, this means, as we said earlier, for the antisymmetric sectors, these are all the antisymmetric sectors states that you could construct at orbifold point. If you identify the correct primaries, then all the primaries will be fortuitous. So this is a very strong consequence. I'm checking whether this conjecture is correct right now. And okay, so since I only have 7 minutes, so let me try to explain how to construct a fortuitous state at larger n using the small n data. As we said, that fortuitous states will lose the BPS status after certain n. A natural thought is whether you can, do some composite of fortuitous state and other states to make it remain BPS, even after n star. For simplicity, let's just think about the composite of 2 BPS states. Consider 2 single cycle quarter BPS states. One is of length W1, another is of length W2. The naive product states will be it will be a 2-cycle state with excitations as before, as above. So you might say that this state cannot be Q-closed because we explained earlier there are joining process. So it's not guaranteed that a product of BPS states will be BPS. However, if you manipulate with the right moving Clifford algebra, you can project the state such that the joining process is forbidden. Therefore, for these special sectors, the supercharged action will obeys the Leibniz rule when acting on the Therefore, we can get a quarter BPS composite states. So this means the BPS states as small n could be used as ingredients to construct larger n BPS states. Is there any questions about this part? Okay, good. So the projection is not something that weird, but if you recall the supercharged quotient complex at n equal to 2, we said that there are 2 special sectors, there are 2 special antisymmetric sectors. You cannot be mapped to anything and nothing can be mapped to it. If following the similar construction at larger n, you can identify states that couldn't be joined just simply by the right moving selection rule. So therefore, there could be 3 types of composites. So you can make a composite of monoton and monoton, so it's still monoton. And you can make a fortuitous and fortuitous, so this could have some interpretation as multi-center black holes, and you could also form the composite as fortuitous and monoton. So a fortuitous state becomes non-BPS after certain n star, and in the larger limit with n much bigger than n star, we expect it to be dual to a massive string excitations in a vacuum S3 times S3 times T4. Assuming that W1 is much larger than the W2, W1 will be the one corresponding to the monoton, and we expect that that monoton is a monoton state corresponding to the superstrata geometry. So this gives an interesting phenomenon. So somehow a massive, so a non-BPS operators in a boundary, if you probe it with to some superstrata geometry, then it could remain BPS. Okay, formalize it. So the fortuitous and monotone state describes non-BPS state probes a BPS background created by the monotone state, and it remains BPS. We want to interpret this as a BPS string, and this is an example where the boundary states will tell us how the bulk solution should look like. There are multiple natural and difficult directions to explore. For example, at least a few directions. You can construct more fortuitous states to probe the nature of black hole microstates. You could investigate the chaos in the quarter BPS sector using the criteria in Min's talk. One could also test the non-renormalization conjecture at n equals 3 to gain more confidence for the fortuity at n equals 3. There are more, but before I end, let me make a comment about the current draft on the archive. So in the current version, we claim to find many fortuitous states in the n equals 2 theory. We were not careful with larger n equivalence, and therefore some fortuitous states that we printed on our paper are actually monotone states. So, but we will update our paper soon. So hopefully I can do it as soon as possible. Thank you. That's all I want to talk about. Thanks.
Can you explain a bit more about this fortuitous monotone mixture and so on and so forth? Can you explain it a bit more? I mean, it was a bit fast, so maybe you can.
Yeah. So actually, the idea is similar to the n equals 2.
Was it also fortuitous states or not? What's
it's a fortuitous. Let me go back to the n equals. Actually, do I have the n equals 2? The intuition actually is really based on this 1,1A sector, because as you see that the supercharged cochain complex I wrote down here, this 1,1A couldn't be mapped to the maximum utility sector. So there will be similar phenomena happening at a larger n, that you could find some W1, W2, that if you take an appropriate arrangement of them, they couldn't be joined to a W1 plus W2 just by the R-charge conservation analysis. So the joining process will be forbidden. So this will render the supercharged action has a Leibniz rule. So this makes a composite possible.
And then how does it supposed to look in the bulk? Can you go back? You had some comments about some probe.
Oh yes. So yeah, so intuition here is a fortuitous state after given n star will not be BPS. So it's like you have some kind of bulk field that is dual to this non-BPS operator probing the maybe superstrata geometry. Then somehow the whole system is still BPS.
Because we have some solutions, for example, which are bubbling geometries, and those sorry, wait a minute. One more. Bing, bing, bing. Okay, so we have some solutions. I mean, we had them 20 years ago, Nick and I, which are bubbling geometries. And bubbling geometries, for example, they only exist for some specific values. So if you fix Q1 and Q5 and you fix the topology, so if you have a fixed topology and you fix Q1 and Q5, you cannot put a QP except for of a given value. If you put anything more, you don't get a solution. You actually get a non-supersymmetric. You can get a non-supersymmetric solution, but you don't get supersymmetric solutions anymore. So
that's interesting. So there might be some similarities here.
The thing is, when you're saying that when you have a non-BPS probe on a BPS background.
Yeah.
So with this fortuitous monotone state, so this would be a non-BPS. I mean,
so if you combine them together, it will be a fortuitous. But if you separate them, monotone is BPS, but because fortuitous is on. Okay, I'm talking about the fortuitous at small n, but I want to extrapolate it to larger n, so you will not be BPS at larger n. But I'm saying that if you do some appropriate combination between this non-BPS state at large n and the monotone state, then you can still find the BPS state. And that state at the larger n is still BPS.
Oh. So would this be some excitation, I'm just wondering. why would this be a BPS? So normally the BPS the superstrata are just some bubble. I mean, it's just some empty space. You'd put this as an extra. So I'm just confused. What would be this extra probe?
This extra probe, it's not BPS. Okay, how to phrase it?
It's
So
plus space, or
BP,
I mean, I'm a bit confused. Non BPS where? Because I can put a different in empty space. It's BPS. I put it in global ADS. It will not be BPS anymore unless I put it on a very weird trajectory. So what do you mean by non BPS? That's
I mean BPS. When I mean non BPS, I mean like if I just put it on the vacuum ADS time T4.
The probe that would have been non-BPS if it were in the vacuum.
Uh-huh.
The conjecture is that if you put that probe instead in non-trivial microstate geometry, it would be BPS because of the interaction with the background.
Picking up some other
Interesting.
background from supersymmetric.
Interesting. So those would be some solutions. Okay, but that's a very interesting.
So what's the
No, so this probe again, so he basically has two ingredients. One of them is a superstratum, and then one of them is another guy, which would be a non-BPS object.
Sure.
But if you put the non-BPS object in the superstratum, interaction with the whole thing will be BPS. Now, what's confusing me is that we get most of the superstrata using killing spinners, and both objects we put there, they have the same killing spinners. So I'm a little confused about this non-BPSness. How would it work? Because most of the superstrata are killing spinners, and if these guys don't preserve the same killing spinners as the superstratum, the empty space killing spinners and the superstratum killing spinners are a subset of the empty space killing spinners. So if the guy is not supersymmetric in empty space, it screws up the superstratum killing spinners. It should screw up the superstratum killing spinners. But can we get some killing spinners which bend then? I mean, the question is, would this say that fortuitous states? Because again, if we just build things using killing spinners, we just say I have the black hole killing spinners, I'm imposing them on the superstratum, they give me some supersymmetry. If you bring another object and the object doesn't have the same killing spinners as the superstratum, that object would not, naively you cannot bring it in. But then sometimes you can bring an object, you can back react it, and you'll get some killing spinners which depend on position, which are not the same as the black hole killing spinners. But the question is, would this be for the fortuitous states?
Something as naive as the fact that you have to do a self-dual F1 NS5 flux. And if you don't tune the F1 NS5 flux to be exactly self-dual, then you would break the supersymmetry, but maybe by changing some aspect of the superstratum, you have to then compensate by changing some aspect of the NS5 F1 flux.
That's simple.
That's the simplest thing I can think of that matches the data you're describing.
Yeah, I don't know.
Is it obvious that you can actually do this construction? Because when you say non-BPS state in empty ADS, I would have thought it's like a massive string state or something like that. Like, it's not obvious to me that you could understand these just in the context of supergravity, right? I mean, maybe some of them,
I also feel
the discussion would apply, but...
So it seems like somehow the supergravity solution could probe these massive string states, but I'm not sure how this works.
But then you wouldn't construct something by solving a killing spinner equation necessarily if the non-BPS state is something that's not in the supergravity spectrum at all, right?
Actually,
Why? If the heavy string state is big enough, I can always back react it. I mean, I can always construct it. I mean,
that would be the way to do it. But then if it's heavy, then the G Newton is large too. I guess by design that's what you want, but
And why would what about the fortuitous? You're saying that fortuitous would be multi-center black hole. What does it mean? I mean,
I put a question mark here because I don't understand this very well. So naively, I mean, I could think this fortuitous as some kind of black hole and black hole. But so the reason why, I put a question mark here because I don't understand this story very well.
Could this be some bubbling transition to a multi-centered flux?
I think it's a bubbling transition to what's in the flux, exactly.
So in other words,
exactly.
you have some center which is two centers, and then you whack it somehow, and it naturally bubbles to a three-centered solution with a small separation. Maybe it may not be a black hole, in other words, it might be just another microstate geometry with multi-centers.
So there's a whole literature on multi-centered solutions. So again, we've been doing superstrata because they have a nice CFT dual, and we never need the CFT duals of these bubbling solutions. So there's a huge amount of geometries, which are just a bunch of bubbles. And
Are they BPS?
they're BPS, yes.
Yes.
Okay.
But the general dogma in this story is that they are somehow generically lifted. So we focused on the multi-centered one because of the holography, but in the old days, the very first ones we made, we had multi-centered bubbled supersymmetric solutions, but the general dogma is that in the full supergravity, they're at the general point in the moduli space, they are lifted, they cease to be BPS.
But it's not clear. I mean,
And the lifting is pretty mild because some of the examples have been studied in perturbation theory, and the lifting goes a little bit above BPS and then can, in different points in the moduli space, can come back and be BPS again. So might be what you're looking for.
I see.
So they have a long throat, again, they have an ADS2 throat, and then they have an ADS3 throat, the way I'm drawing it here. So, this is an ADS3 throat here, which goes into an ADS2 throat, and then you have these bubbles at the bottom. And the bubbles are just some bubbles with flux. The point is, once you are in a D1, D5 system, and they say, hey, my Q1 is N1 and my Q5 is N5, and you fix the topology here, you only have some discrete choices, and the NP, given N1 and N5 as numbers, NP is not a free parameter. NP, the solutions only exist for some values of NP. If you put an NP bigger than that, they don't exist anymore. So that's the kind of physics which you see in fortuitous states. They exist for some values of NP, but then at some other point they don't exist anymore. I cannot pump NP on the solutions at all.
So if I want to translate this into the CFT language, this means that the energy couldn't be as large as I want.
Sorry?
If I want to translate this into the language of D1, D5 CFT, this means that the energy, like the energy of the operator cannot be as large as I want. So
those guys are not obtained by acting on vacuum. So the whole point about superstrata, you start with global ADS, and you start acting with L-1, so you're putting a graviton gas on the vacuum, and you're just pumping up the vacuum with various modes. And that's what superstrata are. They're basically L-1s in the CFT language. Some combination in some J's. Now, those bubbling geometries, they are not at all like that. We never understood their CFT dual because they cannot be seen as a perturbation on a vacuum. They're bubbling geometries. They're obtained by changing topology. So there are some, we can think about them as either some heavy string states back reacting and changing topology, or something funny happening. It's not. They're not your usual. They're not perturbations on top of an empty space. So that's why on top of global ADS. So that's why those look awfully a lot like fortuitous states. It's just.
I see. It will be interesting to have a more precise statement about it.
These multi-bubbled states have to be states within the CFT, because if you take the scaling limit, you have a nice ADS at infinity. It's part of this conformal field theory. It's just we have no idea what those states are in the conformal field theory. And it'd be really nice to know. It's a big gap in our knowledge.
I see. Yeah, for the moment, I don't have any useful to say because I don't know how these states should look like. But certainly I was a bit confused. Well, I can tell you the thing I was a bit confused at. So I was confused at how to, for example, well, yeah, I was confused at how to interpret this because, even for the N2, it's the simplest case. This is a maximum electricity sector. I don't know if how to interpret other sectors.
About this middle cohomology thing, you said you made this conjecture about this R charge concentration. Is this what is this based on? Is this based on n equals 3 computation or?
Oh, this is based on N2 computation because you see, so as I said, all the primary quarter BPS states are in these 3 blocks.
Right.
So it's not just sharply concentrated; they are literally at this middle point.
Sure.
And
sure.
I want to make conjecture at N2 3 that it will be sharply concentrated at the middle. But I'm checking it right now. Hopefully, after a little bit of time, I will not say it's a conjecture. Well, but anyway, yeah, I'm checking it.
Okay. So even for n equals 3, you are still checking if this is true.
For into 3, I'm checking, but there is an intuition. I was told that I shouldn't say too many imprecise things, but the intuition is that if you think that twist 2 operator is chaotic enough, then in principle, so for all the states that could combine together to form a long multiplet, then why not if it's really chaotic enough?
Can you say it again?
It's just some random thing I wanted to say that.
Yeah.
So at n equal to 3, I actually did all before the degeneracy computation. So of course, this 1, 2, the degeneracy of 1, 2 will be much less than the 3. And I'm saying that if the deformation, that twist 2 operator is random enough, then hopefully you will lift all almost all the 1, 2. But this is just a random stuff.
Okay. And there used to be, there was some analysis of quiver quantum theory where they discussed the moduli space of Higgs branch based on the cohomology, and they found something similar happening. Almost all states are in the middle cohomology of
interesting.
the target space. Do you see any relation?
I don't have any comments about this, but I will refer you to the paper by Yiming Chen, Qiming Chang, and Zhengbin Yang. So their paper on the fertility in SYK model, they have a general discussion about this ultra concentration. Right. I actually learned this concept from them.
I think see any connection. So you also have, in your paper with Jan and also Berkers, you had this quiver quantum mechanics, and almost all states are coming from the middle cohomology, right?
Yeah, I think that's a really nice example of something fortuitous, because what's really happening here is when you do this from the point of view of Calabi-Yau manifold, you inherit some of the cohomology from the ambient space, and that's all the stable monotone stuff. But the other cohomology comes from the superpotential on those Calabi-Yau spaces. Yeah. And that superpotential changes structure within. And so all the ground states just reassemble. There's a large number of them, but I suspect this is a really nice example of fortuity.
But why is this related to this middle cohomology?
Because that's where I'm pretty sure that's where the let me just see. The middle the fact I know is the middle cohomology is given by a vanishing of the class of super, given by critical points of the superpotential created on the critical point mechanics. And the structure of that superpotential is a sensitive function of all the parameters. But the fact is that all its critical points just move around like crazy as you change the number of hypermultiplets or whatever you've got. And that's the middle cohomology. That's where the huge number of states comes from. So there's this the calculation is done by doing some cohomological calculation of a bunch of quadrics inside some large set of products of projective spaces. And so the cohomology so the interesting thing is the cohomology of this manifold defined by the vanishing of the critical points of the derivative superpotential.
Yeah.
So you calculate the cohomology, and there's a pile of boring cohomology that goes, which comes from the ambient space. And then the incredibly rich cohomology comes from the way that this hypersurface that you've built in this, or the surface you built in the
in Calabi-Yau.
I'm certain that depends on those are all fortuitous states, and it'd be really nice to see that. And there's this tour de force calculation Greg does with that F4 paper where he actually calculates the Euler characteristics as a function of various ends that turn up in the equivalent quantum mechanics. And there's this situation where the number of ground states changes from essentially quadratic in the numbers of quiver lengths, and then it goes exponential. Two is, there's A, B, and C, which is the number of quiver legs, and it goes to A times B plus B times C plus A times C, and then it goes to 2 to the A plus B plus C, depending on if A, B, and C satisfy some triangle inequality. And it's a very crisp change. Anyway, it strikes me as must be a classic example of fortuity.
I see. Yeah, here the cohomology is not really related to the target space cohomology, right?
No, but there was. No, this is not how. Okay, the cohomology I'm talking about is. Okay, I'm trying to remember the details. There's a whole bunch of complex fields set up by the quiver quantum mechanics, and they satisfy some. There's some superpotential, which then give them. I can't remember.
Can I ask about this non-uniqueness?
Speak louder.
Harry, can you take us back to this non-uniqueness of the lift from one
Yes.
body of n? I just was a little bit quick. I wanted to ask for a detail on that.
Sorry, I didn't hear it clearly.
Okay, I'll wait till you find the slide.
Okay. I just wrote a simple line here. The lift is not unique.
Yeah, can you go back a little further? You were just before this. Yeah. So here,
Okay.
this was very nice. So you were showing us that if you want to start with a state which was BPS at n equals 2,
Yeah.
then you have to ask this question in your middle equation, whether there is some state at n equals 3, which can contain this extra piece in the 2,1 sector.
Yeah.
Okay, so in this language, it's possible to state more explicitly why this is it for this reason that the lift to n equals 3 is not unique, or is this some other reason?
So I think you could think about actually maybe if you think about the projection, then it's easier to think about the lift because you can have any kind of non-trivial excitations of this 2,1 as long as there is a non-trivial excitation, then it will be projected to nothing at n equals 2.
So is the question whether there is more than one 2,1 state which will cancel the action? Next
Oh,
one.
I see. That's a good question. I'm on the investigation of it. So our definition is as long as there is one such state exists, then yeah.
Yeah. So on the next slide, when you say that not unique, is that exactly this non-uniqueness of the state at 2,1?
I guess what I had in mind when I write this slide was that the thing I was just saying that I have this projection. So if for any kind of non-trivial excitation, the non-trivial excitations in the the trivial sector, then you will always be projected out. Another way to think about this, since we are focusing on the cohomology, so there could be a bunch of Q exact term that modify your Q closed state.
Okay, but from that point of view, you're saying the lift might not be unique, but I think you're claiming the lift is not unique.
I see. Okay, I should change it to a lift might not be unique.
Okay, might not be unique. Okay, so it has not yet been proven whether the lift is unique explicitly.
I think the problem is the numerical check can only go to a certain order of energy. That after that, then I have to make a conjecture.
Okay, but have you seen examples where the lift is not unique?
Let me see. Okay, perhaps I should get back to you when I find an example. It's not unique. Yeah. So as I said, that our previous draft there were some errors, and we were in the process of trying to fix that problem. So after I submit the current new version, then I hope everything will be clear. Yeah.
Okay, thank you.
Yeah.
There's a question.
Sorry
There's a
about
question by Yoav, and then I think we should take a tiny break and move to the next talk because we're already in the interval for the next talk. Yoav?
Yeah, my question is, how do you distinguish boundary gravitons from ordinary gravitons, both from a bulk perspective and a D1, D5 perspective?
Oh, from the D1, D5 prescriptive, so you could think about these boundary gravitons as some kind of local algebra, like because you have this contracted large into 4,4, then there are global algebra and there are also local algebra. So I think the statement is that if you act this local algebra on the states, then it sort of corresponds to dress the boundary graviton on these multi-gravitons. But certainly, if you wait for the next talk, I'm sure they will give you a better answer because essentially they will give a very comprehensive review of it, I think.
Okay, so maybe we should close here and thank again Haoyu again for the nice talk, and we'll resume at 5 o'clock sharp here, so 8 minutes from now. I'll leave the YouTube going because it's very hard to restart. So you guys, if you want to say something, I mean, don't talk bad things about Trump on the YouTube, especially in America.
Thank you.
Thanks again. Thank you.
Can I ask you for comments on the Ramon sector? Like, do your conclusions change? Yes, we can spectral flow, but people would seem to think that the bulk physics is quite different. Like, people think that you can have very large supersymmetric black holes in the Ramon sector, but then I've seen some people in the literature, and maybe these were older papers that I've gotten confused by, but some people say that the NS sector can't have large BPS black holes, which might be totally wrong. But if we're interested in this fortuitous monotone classification as a way of understanding the black hole microstates, how does the Ramon sector compare from this point of view?
I guess I don't really have. Okay, go ahead.
I don't understand the question. I mean, the spectral flow is an isomorphism.
Right. Yes, I agree that the spectrum will be the same.
In the bulk, it's a large coordinate transformation.
Yeah.
So anything you find in the NS sector, just do a large diffeomorphism on it, and it becomes a state in the Ramon sector. So the bulk geometry locally is no different.
Okay. Some conclusions will be different in my talk on Friday, but maybe not relevant for this.
All right, I'll look for
it. You can grill me at that point. Yeah.
Right. Yeah. Right.
I guess I'm confused by just the nature of the whole enterprise. So I okay, it's hard to find BPS states. I think it's sort of like a coarse-grained conclusion that they're fortuitous in the sense that if you find one, you've sort of found a needle in a big haystack. But I'm more confused about what I'm supposed to learn about black holes, because I mean, suppose we take
that gives you G minus a half.
Suppose we take some state which is fortuitous, and I change n a little bit. Well, first of all, I don't even know exactly how to compare states and theories with different n. They're just different theories. And so exactly what I'm supposed to mean by looking at something that's fortuitous, does it? So suppose I find a fortuitous state at some value of n, and then I change n to n plus 1.
Yeah.
Are the fortuitous states supposed to be sort of nearby in some sense, that they're like small deformations? Do they change a lot?
So I think the thing that currently I could say is that as I said, as I mentioned in the talk, if you find the fortuitous state at angle 2, then you might wonder how it looks like at angle 3, whether it's still BPS or not. So at angle 3, you can modify the previous operator by some new operator, by some new operators that will not survive under the projection. So it's kind of arbitrary, but so the question I want to ask is whether you could find a possible combination to make that state BPS. If you couldn't, then this state will be BPS automatically. But certainly there are some ambiguities on how the lift goes if you couldn't find a lift.
But I guess part of the confusion is, okay, so suppose I increase n. Suppose I'm trying to compare two theories with n and n plus 1. Okay, and so yes, the number of fortuitous states differs from one to the other. but my naive expectation would be that, okay, they're all black holes at sufficiently large n. And, it's just that, okay, some black holes get lifted by a little bit, but they're still black holes generically. So what is the property of fortuity? Why is it important? If the state that got lifted, okay, so maybe it got lifted by some tiny amount and now becomes a non-BPS state, which is okay. We can stop talking about it because it's not BPS, but somehow one's making some big deal about the state getting lifted, and I'm just confused about why, from the point of view of black hole, somebody who's thinking about bulk black hole physics, why is this an important distinction?
From black hole perspective, important distinction.
A slightly non-BPS black hole and a BPS black hole, and one is fortuitous and the other is not. So why am I supposed to care?
I guess I actually, for the moment, I couldn't really give a very good answer, but I could go back to this previous slide I was talking about. So this is still the includes 2 to go to includes 3. So if you lift your maximum utility sector at includes 2, you will go to this 1,2 in includes 3. And so the right moving hour charge is a bit different for the maximum utility here. So I guess the way I want to the way I think about this for Twitters is how you provide a mechanism on how this new BPS states could emerge. Yeah, I think I didn't provide enough thought about when they vanish. Yeah, sorry, I don't have a good question, but if I have a good sorry, I don't have a good answer, but if I have a good answer, then perhaps I could write you an email to say that.
Okay, I would appreciate that. Thank you.
Yeah, thanks.
Well, I guess, I mean, they're more interesting BPS states than the monotone, at least, right? I mean, we could, maybe we don't, a BPS black hole or a non-BPS black hole is not so important to us, but it's, it's some kind of interesting quantum gravity effect that knows about the quantization of n. But, okay, yes.
Okay, is anybody hearing us? Oh, pointer. There's a pointer here somewhere, but I don't know where it is.
Do you want a point? Do you want a pointer that works on the screen, or you want a pointer that works on?
Well, this is a pointer. Sorry. But you may need the
Feeling will still on the screen, if that's what you're. You may want to use the arrow in the pressure.
actually, no, you can. See,
The what?
you can. No, I thought. No, it needs to be connected to something.
What about just doing this?
Oh, voilà. Good.
I know it's painful, but that's
Painful for you.
Well, no, I mean, is there a fancy? Maybe it's going to be paired with the computer.
Oh, with his computer.
Yes.
Ah, yes, but I don't know how to do it. You need a stick.
Oh,
You need a stick.
there's a sticky.
Oh, there's a stick here. Do you have a USB to?
For the perimeter thing?
We don't have a USB.
Oh, that's an alternate, actually. That's not a.
Working. The same.
Yeah.
No, don't do it now, do it, in the day, so it's fine.
Oh, hide the bar at the bottom.
Doesn't matter.
Oh,
Can we get
let's
that
put
back?
his computer on, actually, sorry, let's change it.
Check
Place connecting? What the hell have I done? No,
many people
now he's done something.
No, just.
How do we get this back?
Yeah. This one is sharing, yeah.
Yes, that one is, what's this one?
This one I'll highlight him. This one is the one here, and I'll just shut down.
I can find anything. On my keyboard. I've got my hand in my pocket for a reason, so I can't be implicated.
And you have this here, right? Okay, so now there will be a.
Stay away from it.
Oh, is that Marcel's screen? Very laggy.
Your computer has to talk to the. Tell your computer to talk to the.
What is?
That's the Zoom, but the one here talking to this projector, we don't have it. Oh yeah, this one should drop from Zoom because I put your thing there. Okay, so that's a bad idea. So this one, okay, forget about it. Okay, let's put this here. And you have this guy back on Zoom. Your thing is supposed to talk to this thing. Can you put your screen share or screen something? Can you tell it to start?
It is.
Extend but extend your screen or put a monitor.
It's on duplicate.
Sorry?
It's on duplicate.
It's on duplicate, okay, because it doesn't see this thing, machine doesn't see it. This is your Zoom, so your Zoom goes there. Whatever people see on Zoom goes on the left. But yeah, but this is HDMI. Yeah, if it has an HDMI. Oh, don't do that. It's right. Yeah, source HDMI pas de signal. So if you just put source search. Why is HTML2? Yeah. No, it's not seeing anything.
Something gets screwed up.
Oh, your computer doesn't see HDMI, so let's do this now. Let's put this thing in. Maybe it's better, but I don't think it is. I'm afraid it's not. Okay. At this point, your computer is not telling anybody what to do, so.
Something. Yes.
Okay. Okay, so this is your screen now. Yeah, great. So get rid of the upper tablet if you want. I don't know how to do it. Okay, great. So where's the Microstate? Are you guys hearing us? Matthew, how are you? Are you hearing us?
Uh-oh, now we got the sounds.
Yes.
Oh, you are. Okay, perfect.
Good, okay.
Okay, so for the second talk, we're very happy to have Marcel Hughes, who will be telling us about fluctuating in supergravity.
Okay, thank you very much to the organizing a nice workshop. It's always very nice to be back actually. So I'm going to talk about again the D125 CFT and again some aspects of this fortuity story, but refining our notion of it and how we can capture these states into some index or partition function. And I will also comment as well about how our paper will also change a little bit on arXiv in the near future, along with the previous speakers. But this is working in collaboration with Zhang Shikamori. So yeah, I will briefly, hopefully review the D125 CFT again. But I need to set some notation because my notation is different from the previous talks. Then I'll discuss PPS states, supergravitons, and elliptic genera that capture these in the following section. And then I will describe a construction that takes the supergraviton partition function or index and creates a new index or partition function from this that captures a larger number of states. However, states that still behave like supergravitons. And I'll conclude. Okay, I have a obligatory slide about the D125 system, but I'm not going to insult people's intelligence in the audience. But so I start with type 2B string theory. We can back-to-by on a large S1Y and then a string size M4. M4 is T4 or K3. And I will discuss which one of those I'll talk about mostly in this talk later. There's a decoupling limit. You get ADS3 asymptotics across S3. There's a dual 2D CFT. Central charge is 6N1, N5, where N1 is the number of D1 branes that we wrapped on the S1Y. N5 is the number of d fibranes we wrapped on S1Y and the M4. And there goes some supergravity regime, roughly speaking, the large M limit. This system is 2 charged, but we can add a 3rd charge by adding quantized momentum waves along the S1Y. So what is the motivation for this talk? So the rough motivation, as with a lot of other talks recently, is to identify, classify, and study BPS black hole microstates, and using the powerful tools that exist within the holographically dual CFT description. So question number 1, I would like to know what some people call genuine black hole microstates, what others call more typical black hole microstates. What is this distinction from the CFT point of view? Now, it's a very hard problem in general, of course, so we try and use recently some different tools, describing the Q cohomologies of these states, or capturing them within supersymmetric indices. As we've heard, the recent story of fortuity suggests a possible classification based around, in some sense, typicality, along with, as we heard from Newman Cheng, about their chaotic properties. So this talk is concerned with capturing states based off of this classification, but in an index language. It's good to start somewhere, I think. Okay, so as I just said, we roughly speaking have this sort of hierarchy of ways to capture or describe different amounts, different sort of fine-grainedness of BPS states within CFT. So starting at the bottom, you have really just the description of BPS states. These are solutions of this form. They're killed by a Q action. Hard problem in general. You could sacrifice a little bit of fine-grainedness in a sense and study instead the Q cohomologies, where instead you solve the BPS condition, but up to some, where the states are defined up to some Q exact term like this. Or you could go further and you lose, let's say, more fine-grainedness, but you increase your probability of saying something potentially by studying instead a supersymmetric index, which is counter states where you have a relative sign between the bosonic and fermionic states. And I will be working in the index category. The previous talk was working in the middle category of Q homologies. Hopefully together, these tools can say something useful. Okay, so the D125 CFT. It's a CFT dual to the D125 system, and it's very, very strongly believed to be the modular space of the symmetric product orbifold of generically this M4 internal manifold, but I will be from now on sticking to T4. In particular, it was shown by a series of very nice papers by permutations of these authors that the specific place in the moduli space that is where the CFT is exactly described by the symmetric orbifold is dual to string theory on ADS3 cross S3 cross T4, but with minimal NS and S flux. This is a very nice, precise statement. So what is this symmetric orbifold theory? Well, it's built from a seed supersymmetric sigma model with T4 as target space. And the Hilbert space of this seed theory is constructed from 4 bosonic modes and 4 left-moving fermionic excitations, the equivalent of right-moving excitations. Everything right-moving in this will be denoted by a tilde. So, this forms a Fock space. They freely generate because it's a free seed theory. And these free boson fermion modes can be used to construct a C equals 6 N equals 4,4 superconformal algebra whose generators are of this form. L are the usual Virasoro modes, and you have some supersymmetry mode generators, and then you have a R symmetry generators. And the total R symmetry is SU2 on the left and SU2 on the right. And the generators are these 3G generators. So how do you take this Hilbert space of the seed theory and you construct the Hilbert space of the symmetric orbifold theory? Well, you take n tens of copies of this seed theory Hilbert space, and then you orbifold by the symmetric group of order n. This Hilbert space decomposes naturally in terms of what we call twist sectors, which are in one-to-one correspondence with the conjugacy classes of Sn, which we can label by permutations within Sn with fixed cycle structure. So this data n1, n2, all the way to nn basically specifies your twist sector. It's possible to break down the twist sector Hilbert space HP further into a description in terms of these HAs, and these HAs are the single strand Hilbert spaces, and these are strands of length A. And you have some ZNA symmetric combination of these, and you project onto a SNA invariant subsector of this. Okay, so what are these single cycle or single strand Hilbert spaces like? Well, these are the Hilbert spaces of the theory defined on a spatial S1Y, which is part of the base space of the CFT2, which has an A times longer circumference. So now fields and modes have a strand label, is I in a bracket, which tells you which, roughly speaking, tells you is related to which of the tensor factors it originated. And the periodicity on this multiply wound S1Y gives rise to fractional moding. And this leads to lots of interesting phenomena associated with this theory. So what is the symmetry algebra of this symmetric orbifold theory? Well, you don't preserve all n copies of the C equals 6, n equals 4, 4 superconformal algebra. Instead, you preserve the diagonal subgroup. And the generators of this I denote with a T here in this talk and in our paper, which denotes what we call a total mode. It acts diagonally on the strand structure. In fact, these generators here on the left and on the right, they generate what's known as the small n equals algebra, but for this T4 theory, which is enhanced by the addition of these generators, again, total mode generators, and it enhances to a C equals 6n contracted large n equals 4 algebra. So these total modes, which will play a very important role in this talk, for example, for the Virasoro generators, these are defined just as this sum of the individual strand generators. So it acts diagonally. And for both of these small and contracted large algebras, there's the same global subalgebra, the anomaly-free subalgebra, generated by this subset of generators. Okay, so what does the spectrum look like? Again, as usual, we use the eigenvalues of the constant subalgebra to label states, and a particular subset, special subset of these states are chiral primaries, and they have conformal dimension h equal to their R charge spin j. And they, in other words, preserve some two of the two states. Okay, so we can classify these states very simply in this particular theory, this T4 symmetric orbifold theory, and K here is the label for the twist, for the strand length, and you can simply classify them here. There are a finite number per strand length. These are the left-moving chiral primaries, and there's the analog on the right-moving chiral primaries. Generically, you take any combination of those, and you have a chiral primary. The minus sub 1, k equals 1, is the NS, the unique NS ground state with h equals j equals 0. I will be, throughout this talk, working in the NS sector. Okay, so let's consider the half BPS spectrum. From the language of the symmetric orbifold theory, half BPS spectrum is super simple. You take any left-moving chiral primary, you take any right-moving chiral primary, and this is half BPS. As was shown by Jan de Boer quite a long time ago now, these states are in one-to-one correspondence with the KK spectrum when you reduce on the S3 of AS3 cross S3 as n goes to infinity. At finite n, you can still match, but you need to introduce the string exclusion principle. So generic multi-particle, these states here, these half BPS states here are effectively single particle excitations in the bulk, they're supergraviton excitations. The generic excitations are multi-particle half BPS supergraviton, states, and I denote them like this, where the product is almost free, except that I have to introduce this string exclusion principle. The phi here just denotes any of the chiral primers that I had on the previous slide. Okay, so half BPS, maybe not so interesting. It's protected, and we've learned about them already. So let's move on to the quarter BPS spectrum. What happens there? Well, again, from the symmetric orbifold theory, it's very simple to describe. You preserve still the supersymmetries on the right by having a chiral primary, a right-moving chiral primary, and then you add any excitation you want on top of the left-moving state. And this breaks generically all of the left-moving supersymmetries. So I can write any generic quarter BPS state in symmetric orbifold theory like a subset of these, basically a subset of left-moving excitations I can add, are the excitations of the global subgroup, the anomaly-free subalgebra, on top of one of the half BPS states. And I can take generic products of these to create the most generic quarter BPS multiparticle supergraviton states. Again, subject to string exclusion.
Marcel,
Yes.
do you also need to impose a gauge singlet condition on the states?
Gauge under which in terms of what group?
There's a UN1 times UN5 gauge group.
Right. I'm considering only the sector that's not charged under the default.
Okay.
That's gone, right? So that's some very UV thing having to do with D-branes. This is some low energy conformal field theory that is the infrared fixed point of that UV gauge theory. So all the gauge symmetry is gone in that. So the only remnant of it is the symmetric group. And he's explicitly taking account of gauging the symmetric group symmetry.
Mm-hmm.
Which,
Is that okay? Okay, I'll move on. Thank you. Okay, so if that was the full story for quarter BPS states, life would be quite easy. However, it's not. And you get some intuition about the fact that this is true by looking at the in this particular regime of conformal dimension and n scaling, large n scaling, the density of states of BPS states in the symmetric orbifold theory has a very, very fast growth, Hagador-like growth, whereas the density of states from the CFT index grows much, much slower, and this index is valid at any point in the moduli space of CFT. However, it can have, of course, -1 to the F cancellations, which goes on to fermions. However, one can also look at the KK spectrum, which is what survives in the large n limit, and this is not an index, it's a count of states. This also grows very fast, but slower, parametrically slower than the density of states at the symmetric orbifold point. So part of this discrepancy is due to a phenomenon called lifting or multiplet recombination, where so here I'm denoting by characters, but I can describe this also in terms of the multiplets. This is at the symmetric orbifold point. I have a left-moving long character. I have broken all the symmetries because I was talking about quarter BPS states. And here I have a combination of right-moving short multiplets or characters, which combine in a very specific way to give a completely non-BPS state, and therefore the state is lifted. You get an anomalous dimension as you deform the symmetric orbifold theory away from this free point. So this phenomenon leads to this discontinuity in the BPS spectrum of the D125 CFT as you move away, even perturbatively away from the symmetric orbifold theory. This is a very interesting subject, but I will not get into this in detail. This talk is just to say that you can't directly necessarily work with BPS states at the symmetric orbifold theory, even though they were very easy to write down. Okay, so of course BPS spectrum is not protected, so Instead, I will study an object that is protected as index, and the definition of which I give here. If you ignore for now the red part, I have the definition of the elliptic genus, which is an index for a theory, a CFT with at least n equal to supersymmetry or superconformal symmetry. I have a trace over the Hilbert space with a -1 to the fermion number, and then I have fugacities for the L0 and the J3 0. And this elliptic genus receives contributions only from BPS states, so that's nice. It captures, it doesn't capture non-BPS states, and also it has the property that lifted states, their total contribution, the total contribution from the various multiplets that pair up and recombine, they cancel in total from this object. In other words, this object is protected and it doesn't care about this discrete jump in the BPS spectrum away from the symmetrical point. However, for the T4 theory, it turns out that this elliptic genus vanishes because you have right-moving fermion modes, which for any given left-moving state, you will have this degeneracy of right-moving fermion modes, which in total, the contribution to the elliptic genus vanishes. So this is not the right index to use for this theory. So instead, the modified elliptic genus was introduced. This is the correct index to use for this theory, and that adds in these pieces in red. In other words, it looks maybe fancy, but it just soaks up the degeneracy coming from these right-moving fermion modes. So this is the index that I'm going to discuss in this talk. And here I've given it, although it's defined in the top, I've given it here as some operation acting on the partition function, just because that is the mechanism we're going to use to construct it. The one fairly intuitive question that you want to ask is that, okay, so I have this object that captures the BPS spectrum. What are these states? I know I have some supergravitons. These are subsets of quarter BPS states. And where are these in the spectrum? And in these two papers, the first one by De Boer was actually for the K3 theory, but then this was done first, and then the Anderson and Moore-Strominger papers for the T4 theory. And they compared the CFT modified elliptic genus, so for all quarter BPS states, with those of the supergraviton type. And they found that they agree at the level of the index below a certain conformal dimension, which is n scaling. I refer to this as the Bohr bound, and this is demonstrating what this looks like for the simplest case of n equals 2 theory. So this plot is for the difference between the CFT and the supergraviton modified elliptic genera. Of course, this is very low n, but the green horizontal line is this Bohr bound, and you see that there are no states below this bound as expected from their results. The blue curve is the BMPV parabola. Black hole states lie within this parabola. And these labels with these numbers are telling you about the sign degeneracy specified in this index of the remaining states after this subtraction of the supergravitons. So the initial motivation of this work was to try and understand this picture better, of course, for general n. What are these states that are up here? These are not corresponding to supergraviton states. They're still quartz BPS. What are these? How can we understand this? And the recent ideas of fortuity have made this potentially posing this question in an even stronger way. So as I will not cover this in any detail since we just had a talk about it, but this recent idea is an idea of classification or categorization of BPS cohomologies based on their behavior as you vary n, as you jump between theories, different values of n. And roughly speaking, the monotone cohomologies exist for any value of n, and then there is a smooth large n limit and a clear bulk interpretation in terms of interpretive supergravitons, or if you have a large enough amount, this is this backreactor superstars solutions. And then fortuitous cohomologies, which are a bit mysterious at the moment, but they have this property that these cohomologies only exist for each of these fortuitous cohomologies, there exists only a finite range of n for which they exist, i.e., for which the states are BPS. So what are these? What are the states in those cohomologies? What are fortuitous states? Are they typical black hole microstates? The counting problem tells you that they are typical black hole microstates because they account for the overwhelming majority of the black hole entropy. So how can we capture the fortuitous states within an index? That is the question, basically, of this work. And the fortuitous index would be defined as simply the CFT index minus the monotone index. It's much easier to construct these monotone states, so we can, by inference, construct fortuitous. So the question now comes to what is the monotone index or partition function? So a very natural guess is the following. The monotone index is simply the supergraviton index or partition function. And this is true in other theories where this has been studied. However, as was pointed out in the previous talk, we're still trying to understand this, but it turns out life is more subtle and more complicated as usual in the D1, D5 system. And this is not true. So I put a question mark here and the answer is no, this is not the case. But the goal of this work is to construct the proper monotone index and thereby proper fortuitous index. Okay, so that's motivation, but we came at this from a slightly different point of view. In other words, yes, this picture here at the bottom is very nice, and there are lots of states here that are not supergraviton states, but there are more than just bulk supergravitons within supergravity. So can we know about them, we have intuition about them, so can we add them in? Can we create an object, an index that captures not only the supergraviton states we already understand, but add in additional states that are dual to things we already understand in supergravity. So an example of those are sometimes referred to as singleton states. And these are CFT state realizations of boundary diffeomorphism modes that do not vanish at the AS3 boundary. And of course, all of the N=4 extensions of these morphisms. These are obviously studied a long time ago, Brown and Henol, but much more recently by combinations of Lunimator and Turton in a series of papers, and they're studying this in the bulk solutions that have some of these singleton excitations in them. And there was also a nice paper by Stefan Druster and Rolf Hughes. Okay, so what are these states in the CFT? So it turns out their description is quite simple. The description corresponds to a total affine mode excitation. Total was of this diagonal subalgebra. And affine means the N=4 superconformal algebra, as distinct from the global subalgebra. And you take any of those, for example, the Virasoro generators, L-N, and you act on a generic supergraviton state. And of course, the total mode acts diagonally over the strand structure within this supergraviton state. And for n greater than 1, this is not a supergraviton state, it's a singleton excitation. In the bulk, the idea is that you have still your supergraviton excitations inside the bulk, but then on top of that, you have boundary excitations. And you can make, for example, n or the conformal dimension as large as you want. So it also background description of supergravity. So if you want to make a precise counting of states that are realized within ADS3 supergravity, we really should include these singleton states on top of the already understood bulk supergraviton states. And what we will do is we'll take the known supergraviton partition function or supergraviton index, and we will add to these additional singleton states, and the resulting object I will refer to as the generalized supergraviton partition function or index. Okay, so I have two comments here at this point. One comment is that might potentially seem rather exotic, but a very small subset of these were in fact already sort of partly accidentally counted within the supergraviton index. For example, if you act, so these J plus minus n plus 1 for n greater than or equal to 0, these are affine generators, not global subalgebra generators. If you act on this very, very trivial NS vacuum state, it has strand length 1, then using the superform algebra, you can rewrite this in terms of purely global subalgebra generators, L minus 1, acting on a different half BPS state. So by accident, some of these states were counted in this form. However, there's a very, very small subset, since I can put any other supergraviton state here, and this is just not true. Okay, comment 2. It's at the time of writing this paper, it was not yet understood. Some of the points that were pointed out just now in Haoyu's talk were not fully understood. And because total modes have an independent definition, it appeared as though you could not easily move between theories of different values of n within the singleton subsector, and therefore they appeared to be rather fortuitous. However, in fact, now that this concept of monotone and fortuitous states is in the process of being made a bit more precise for the D1, D5 system, it appears that these singleton states are not fortuitous, they're in fact monotone. So this will be updated in our paper, but it still stands that instead of finding singleton states that we believed to be fortuitous, now that we believe they are monotone, we're in fact constructing the hopefully the full monotone index of partition function. And this is related to the singleton states being representatives of finite n monotone cohomology classes, which at infinite n, as Haoyu pointed out, they are likely become equivalent to supergraviton. So our goal is therefore the motivation retroactively is now to construct the full monotone index. So how do we do that? It's very easy to say. Take an index that captures supergraviton states and add in extra states, which we call singletons, and get a new index. That's very easy to say in words, but one needs an algorithm or some justification for any procedure that one makes up. So for now, let's consider a toy example where you only have Virasoro symmetry. So I only have Virasoro generators, L minus n, and for any non-vacuum Virasoro primary, formal dimension H, the single sort of, in quotes, supergraviton states are simply of this form, where I act with L minus 1, which is the only part of the anomaly-free subalgebra of Virasoro algebra. And I can capture these single particle excitations by a partition function of this form. Each of these terms here is adding an additional action of L minus 1. So these wrap up into a partition function. This is nothing, of course, but a global character. This is a Q expansion, and using these coefficients in the Q expansion, we can write down the generating function for the multi-particle states in this way. This is a generating function where P is your Fugasti that's counting the number of H states. The analog in the real setup is that this P is counting the number of the different strands that you have in your state. Okay, so now we have in quotes, a supergraviton partition function. We now want to generalize this by adding in also the action of total Virasoro generators. And by total here, I just mean generators that act overall on the various states, rather than individually on each Virasoro primary. So in this subset of states, it turns out there's a one-to-one correspondence between global primaries and Virasoro primaries. And so using that, we can put forward this procedure for taking the graviton partition function on the slide and adding in these additional states. So step number 1, decompose the multi-graviton partition function to a sum of global characters. This is essentially identifying the set of global subalgebra primaries. At least, and because of this one-to-one correspondence, it also identifies at the level of counting the set of Virasoro primaries within this subset of states. And now step 2, promote each of these global characters in the decomposition of your partition function to its corresponding affine, or Virasoro in this case, character. So that process is given down here. So this sounds not too bad. This works in this example, but it's a toy example. So what about the full example? Well, before moving to that, one notices that there's a slight flaw, possible flaw in this argument. So if in this procedure of replacing global characters with affine characters, if 2 global multiplets based off of a primary with conformal dimension H prime and H double prime, respectively, if they are related by the action of an affine Virasoro generator, then this promotion procedure fails. And it fails because when you promote one of these global characters to an affine character, you add in states that are already within one of the other global characters. So you've overcounted. Okay, this doesn't happen, however, with this example, this Virasoro example. So one can hope that we don't have to worry about this technicality. So now I move to the real example, motivated by this toy example. So, okay, we do step 1. We take the partition function for supergraviton states in the symmetric orthofold of T4, and we decompose it into characters of the global subalgebra. And the global subalgebra is now this SE1,1-2 on the left. And this character expansion identifies, of course, the total global primaries. Okay, now step 2, you simply replace each of these global characters with an affine character built upon a highest weight state with the same quantum number. And we refer to this step as promotion. However, as feared or foreshadowed in the previous slide, this leads to an overcounting of states in this example, so we do have to concern ourselves with this technicality. Okay, how do we see that this happens, this problem happens? Well, we can focus in on the single strand half BPS supergraviton states. And as I said before, these are easily characterized. Per strand length k, you have 4 of these with different quantum numbers, but they are related by the action of these different affine generators in the following way. And therefore we have to worry, we might have to worry about this technicality I mentioned with the procedure just now. And in fact we do, because these relations between the single strand half BPS chiral primaries induce relations between the multi-particle or multi-strand chiral primaries or half BPS supergravitons, and then also induce further relations between the generic quarter BPS supergravitons as well. Okay, so maybe we can just take care of that. So we propose the following modified procedure. Step 1 is identical. You decompose your partition function into characters of the global subalgebra. But now step 2, we cannot just simply promote these characters to affine characters. We first take step 2a, which is to discard some of these global subalgebra characters. And you discard those that are related by use of the induced relations from this relation here. So you're left, if you have a bunch of related multiplets, you leave just the one with the lowest conformal dimension of the highest weight state, that multiple. So now you've removed all this, all the states that are related by affine modes, the action of affine modes. So now you can go ahead and safely promote all the remaining global characters to affine characters without overcounting. And in doing so, you've also added in back those global characters that you just discarded. Okay, are there any questions at this point before I move to more concrete usage?
Well, just for clarification, in step 2a, are you saying that the boundary gravitons or singletons are somehow they depend on the ordinary gravitons and
No. So what I'm saying is that even after step 2a, there are no boundary gravitons present in this partition function. Those are all introduced in step 2b, where we promote global characters to affine characters. So these are adding in, right, affine descendants, total affine descendants of supergraviton states. So these are nothing but the singleton sets. So step 2a is just removing what otherwise in step 2b, the promotion step, you would end up with double counting of bulk supergraviton states.
okay.
Okay. Okay, so how do you do this in practice, or try to do this in practice? Well, you have to start from the supergraviton partition function. So here I give for T4 the one particle partition function of supergraviton state. It's a bit of a mess, but essentially I have a fugacity P that is counting the strand length, which is K in this sum. And then I have this X function, which details the left moving state information. And then I have this omega K, which captures the right moving state information. The right moving states are simpler because they are just right moving chiral primaries, whereas on the left, it's more complicated. So the definition of omega and K are given here, and and X are given here. And this X is just a combination of global subalgebra short characters, because they're the highest weight states are chiral primaries, and these I call phi. And I've written here the states that the highest weight states that correspond to these characters. So this admits an expansion in all the fugacities of this form. And in order to get a partition function that captures the multi-particle supergraviton states, I should take these coefficients and I should use them in the following way. So I can define a generating function for the multi-particle supergraviton partition functions for different values of capital N, and the fugacity P is labeling each of those. And this is nothing but the platistic exponential of the single particle supergraviton partition function. And the lines at the bottom don't matter too much for this talk, but this is how you define this. So in the bottom line, you can see that the only information in this formula are these coefficients C graviton T4, which came from one particle data. It's fairly simple. Okay, so now that you have this fairly well-known supergraviton partition function, we perform these three steps. And here I'm not doing this for real, I'm just pointing out how you should do this. We'll get to the technical details of actually trying to do this later. So step one is just decompose in terms of the total global characters. Okay, that's simple enough. I take my multi-particle supergraviton partition function for a fixed value of n, and I decompose into a sum of short global characters whose highest weight states are chiral primaries, and a sum of long total global characters whose highest weight states are other primaries that are not chiral. And these F's capture the right moving information, and then the C's are the degeneracies of these. Okay, this is easy enough. Step 2a is to subtract the characters that are represent multiplets that are related by the action of affine modes. So I can take my supergraviton index, partition function, and I can get what I call the reduced partition function. And this reduced means that I perform this subtraction of characters. So
I've just denoted this by changing the coefficients, these d's, which will be smaller than the c coefficients. I will come back to this arrow later because unfortunately that's where all the complication is, but I'm going to for now get away with writing an arrow. This is in principle what you would do. Now step 2b, you go ahead and promote each of these remaining lowercase phi's, which are the global characters. You promote these to these capital phi's, which for me are the characters of the four contracted large n equals 4 superconform algebra. And this defines for you this generalized supergraviton partition function. So that is in principle. However, I now want to specify to the case of n equals 2, just about as simple as I can make it and not be trivial. And I want to describe this arrow here, this subtraction procedure. How do you understand how these relations here between single strand half BPS supergraviton states induce relations between all the other states? So, for example, here, this is just an example of some of the relations between multi-particle half BPS supergraviton states. So not even quarter BPS. This is just the induced relations between the half BPS states for n equals 2. So there are many, many relations, and each of these arrows is just the action of given affine generator. And here are some more. And on and on and on, and you have a nightmare. So this is just the case for n equals 2. So it turns out that this arrow here belies a lot of complexity. Luckily for us, n equals 2 is simple enough that for now, we can just make progress by accepting the calculational complexity and doing the subtraction procedure by hand. So yeah, doing this carefully for n equals 2 yields this generalized supergraviton partition function that I write here, where these capital phi's again are these are short, superscript s is a short affine character, and these omegas are these combinations of the right moving information. The first two terms here come from the untwisted sector of the n equals 2 theory, and the last term comes from the twisted sector. And this gives you a partition function, and from this partition function, as I described before, you can make an operation and find the modified elliptic genus for based on the partition function, and that's given by this result here. So you end up with a surprisingly compact and simple result that captures a vastly greater number of states than originally were capturing. So this captures not only supergraviton states, but also boundary singleton states. So this is very compact, but how do we see what we've done and what this means? So by subtracting the original supergraviton modified elliptic genus from the new generalized modified elliptic genus, and Q expanding, we can see that the first contributing singleton states, those that we have added, they start with terms with fugacity q to the 1 and y to the 0. So this means that you have a total of -8 states, aside the count of bosons and fermions, with h equals 1, j equals 0. But this is very easy to see what they are. We can, due to the nature of our construction mechanism, it's very easy to write down what these singleton states are explicitly. And this is what they look like. You have some in the untwisted sector. The right moving options are given here. And this is the left moving state. And you have some in the twisted sector, again, with some right moving options. And in total, these states contribute this -8q to that we see here. So it just checks that we're doing the right thing. These are singleton states because you have an overall total affine mode that is acting on some supergraviton state here, again.
Marcel?
Yes.
Can you say what is the degeneracy of the singleton states relative to the degeneracy of the gravitons?
The overall number.
Well, not overall number, but for each mode you have different. You have a label of singleton states and a label for supergravitons. Can you give some examples of the degeneracy of the two types of states?
So, for example, with fixed H and J.
Yes.
Yeah, I will show that in a couple of slides.
Okay.
Okay, you can carry on to the next term. So this q to the 3/2 means you have states with H equals 3/2, and here you have states both with y equals plus 1/2 and j equals plus 1/2 and j equals minus 1/2. And you can also check, and we did, that all of these states which contribute this term are also of the singleton type. So the question starts to be asked, if I was to compare the original CFT index with this new generalized index, what are the states that are not of the supergraviton type or the singleton type? These should be quite interesting from a black hole perspective. So here I give the Q expansions for the modified elliptic genera, for on top the CFT, the full CFT spectrum, and then the supergraviton spectrum in the middle, and then the new generalized supergraviton spectrum on the bottom. And you look at the Q expansions, and they, if you compare the first two terms, the first point at which they deviate is nothing but what de Boer told us. So that's expected. And this just means that at some point there are some non-supergraviton states. And this is self-explanatory. But now if you compare the top with the bottom, we see that there is an enhanced matching between these two elliptic genera. Actually, the first deviation happens here at h equals 2, j equals 0. We see that there are 42 or minus 42 extra contributions to the CFT that are not of the singleton or the supergraviton type. So what are those states? Are those typical black hole microstates? Okay, so I'll walk through these figures one at a time. So in the top left, this was the original plot I showed you before. So this is for n equals 2. This is the difference between the CFT modified elliptic genus and the supergraviton modified elliptic genus. So we saw before that there was nothing below the de Boer bound, that's expected, and then there was above that, within the BMPV parabola, new states. And what we wanted to do originally was to say that these were black hole microstates, or more typical black hole. Now on the right, this is the same plot, but now I'm subtracting the generalized modified elliptic genus from the full CFT index. So we have lost, pairing these two plots, we've lost the contributions we used to have at h equals 1 and h equals 3/2. That's what I pointed out in the previous slide. And the first non-supergraviton, non-singleton states occur at exactly here, and you have a contribution of minus 42. So now we've gone from looking at the left picture and saying, I wonder what these states are in the bulk, to the right picture and asking what these states are in the bulk. Now, of course, there's the huge caveat, this is just n equals 2, so, hold on to your chairs. Okay. So, in other words, we see an enhanced matching, an enhanced de Boer type bound with respect to this new generalized supergraviton index. Okay, now to answer the previous question, the plot at the bottom, this plot is a plot of these absolute values of the degeneracies for of states for a fixed value of h, but in the index, and the logarithm of that sign degeneracy, and doing this in turn for the CFT, the generalized supergraviton index, and also the regular supergraviton index, and plotting those. And the blue solid curve is the Cardi type growth, just for comparison. Cardi-like growth for n equals 2. So the CFT index behaves as you expect. It grows like, this is of course the logarithm. So this grows like square root h, square root conformal dimension. And the supergraviton elliptic genus, it behaves a bit peculiarly, but it's a bit of an artifact of this modified elliptic genus not being a particularly good count of states, but it's the best we have, so we will use it. But it grows decidedly not like square root h. And the generalized version is much, much closer in growth for large h to the overall CFT index genus. Now, again, this is just n equals 2, and this is not saying that the majority of black hole entropy should come from states captured by the generalized supergraviton index. That, of course, is not true, right? The typical black hole microstate are not of the singleton type. However, for this very, very low n, they grow with the same power of h, but it's not expected that they would grow with the same power of c, central charge. So this is an observation. Hopefully this answers to some extent your question.
So I understand that the number of singleton states is much bigger than the number of ordinary gravitons for large values of h.
Correct, yes. Okay, so I'm almost, oh, I'm probably over time.
No, it's okay.
Sorry. Okay, so I will conclude here. I will just point out that in our paper, we stick to n equals 2 as a proof of concept of this method. And because the technical complexity in actually making the subtraction process is very difficult. But we focus on n equals 2, but we do not just the T4 case that I showed in this talk, but we also did it for the K3 theory. And there are some differences in the behavior, but I won't, I mean, I could answer questions about it, but I won't go into detail in this talk. So in conclusion, we generalized the well-known supergraviton modified elliptic genus, the index, to also include these total affine descendants of supergraviton states, these singleton states. And this is done by some careful subtraction and promotion procedure, and we did it for both T4 and K3. And this generalized supergraviton index, as Haoyu also mentioned in the previous talk, is conjectured to be the full monotone index for the D125 CFT. So it's not potentially not that easy to get excited about a monotone index, but of course, from understanding the full monotone index via this argument, you can capture the full fortuitous index. So that's maybe a bit easier to get excited about. And performing this procedure systematically for higher values of n is a work in progress, and hopefully in the near future we can report some progress on that. Very interesting, I think, to understand the more general patterns of this object. And then I have a very, very vague statement at the end about what can we use this fortuitous index for. Somehow this is an index which captures seemingly only typical black hole microstates. So one could hope it's something to learn about the nature of these typical black hole microstates from this index. Hopefully something about their properties, their bulk descriptions, for example, maybe their chaotic properties. So I'm going to leave it there for this talk. Thank you very much.
Go ahead.
Well, it seems the graph that you showed with the singleton, it reminds the work by Carl. Let me by Carlip from 1995 about recovering the black hole entropy in 3D from this boundary gravitons. And it seems like a BPS version of this work. Can you comment on this?
I am not familiar with that paper, so I will
Okay.
definitely endeavor to take a look. I don't know if anyone else has any comments about that.
You're not expecting to reproduce the black hole entropy from this boundary gravitons. Yeah, for n equals 2, they look similar, but for large n, no.
Yeah, I don't want to pretend to suggest anything by this necessarily by this closed growth for n equals 2. As I said, we do not expect the growth to have the same scaling with C, right? It's just that we're pointing out they have the same scaling, seemingly the same scaling with H, which is at least something. Hopefully we can say more about this when we systematize this for higher values of n.
Why is it scaling with C? Because I mean, the superstrata, the scaling with
So superstrata are down here. Oh, I mean, they are also in the orange dots, but a very small subset because they are all of the superstrata are inside the.
But you can see any growth for superstrata. You also get more superstrata as you increase H, right?
You do, yeah. Okay, this is an index for starters.
Okay.
And this modified elliptic genus for the T4 theory is not an amazing count of states. If you do it for K3, maybe I have an equivalent plot for, yes. So this is the equivalent plot for the K3 at n equals 2.
Oh.
And so you see that you do have a growth of the supergraviton, and now this is the real elliptic genus. And this growth is more like h to the quarter instead of h to the half, which the CFT has. So this kind of weird behavior down here is really an artifact of modified elliptic genus. Yeah, so it's not a statement about how many you have.
Thanks. You have another question or?
No.
So since you worked at the level of since you worked at the level of states, does this give you explicit states that are fortuitous coming out of your subtraction procedure?
Effectively, yes. It's just it's very messy to work explicitly at the level of states. For T4, for T4, the first fortuitous states are contribute this minus 42, you see here. We did not explicitly write those down, but in principle, if one were to write all the CFT states, then throw out all the ones that are of the supergraviton type and the singleton type, you would find those. For K3, this deviation happens at a lower level, slightly. So this is the equivalent for K3 using the elliptic genus. And you compare the bottom and top, you see that the first deviation happens with a 20 here. So it happens at h equals 1, j equals 0. And so we actually did explicitly write down all of the fortuitous states that contribute this this plus 20. There are many, many fortuitous states, but the overall contribution is a plus 20 q to the elliptic genus. So we did write down those fortuitous states. I just don't know how useful that is, of course. I don't know what you can learn necessarily about the nature of those states. Very messy. So hopefully from this more compact objects, these indices and partition functions, maybe you can learn.
Okay. More questions from people online? If not, let's thank Marcel again. And we'll see you guys in 2 days. So not tomorrow, the day after tomorrow on Wednesday with Matt Heidemann talk followed by Rafael Drake here. Okay, bye.